So today we are going to be talking about determinants. Okay, so let's say that we have some vectors v1 through vn. So these are some vectors in Rn. And then let's say I create a matrix A out of them using these vectors as the columns of A. Okay. Yeah, so I'll be talking about the big formula and also the cofactor expansion methods for calculating the determinant. All right, so the determinant of this matrix A, which we can also think of as the determinant acting on not the matrix A, but we can also think of it as acting on these vectors. So kind of two different ways of looking at the determinant. So what the determinant represents is it represents the signed n-dimensional volume of the n-dimensional parallelepiped formed by these vectors v1 through vn. All right. Okay, so this is kind of a lot to dissect. So I wanted to start with kind of the simplest and most revealing case, which is when n is equal to 2. And then just give me a second. My computer always freezes a little when I'm working on OneNote and sharing it in e-learning. Oh, finally, okay. Because here I've drawn some pictures to help us better understand determinants. So here I'm working in R2. Okay, so I've drawn two vectors u and v, and then here I've drawn the parallelogram formed by the two of them, okay? So in this picture, the determinant of u and v will give us the area of the parallelogram that they form. So area is like the two-dimensional volume, and a two-dimensional parallelepiped would just be a parallelogram. And I also want to talk about the sign, because I noticed, or in the definition, I said that it was the signed volume. So here I've drawn the same picture with the same parallelogram u. But here, for the determinant, we do the determinant of v followed by u instead of u followed by v. So what this is going to give us is the negative of the area of the parallelogram. So to kind of understand why one ends up being positive and the other ends up being negative, here, if I start with u and then follow it with v, so in the picture, like from u to v, that has a sort of counterclockwise sense of direction to it. But if I start with v and then follow it with u, so v and then u, notice that now it has a sort of clockwise sense of direction to it instead. So the sign of the determinant, what the sign measures is the orientation of the vectors or the orientation of the parallelogram. So in two dimensions, you have counterclockwise versus clockwise orientations. In three dimensions, you guys might be familiar with having like a right-handed versus left-handed coordinate systems. So those are like the two different orientations that you can see in 3 dimensions. And that generalizes to higher dimensions, although I don't quite know how to describe it in words when we get to higher dimensions. So I'm just going to pause right now and just kind of ask you guys, do you kind of understand how the sign of the determinant is measuring the orientation of your vectors? Do you have some idea of that from these pictures? Okay. Now, with that out of the way, I wanted to discuss some of the properties of the determinant right now. And I'm still considering the simplest case where I'm working with in 2 dimensions. So I already noted in the pictures above how if I interchange u and v, then I pick up a minus sign. So when you swap the two of them, it changes the orientation, and that's why the sign changes as well. So that's the first property. The second property says that determinant of v and v is 0. And the interpretation of this one is pretty simple. V by itself does not form a parallelogram with any area. So it's saying like the area of this parallelogram is 0, and that's why we're saying the determinant is 0. Okay. So here's a third property of the determinant. Okay, so here we have the vectors u and v, and u is being multiplied by a scalar c. Okay. So when I multiply one of the vectors by a scalar, the determinant is going to be scaled by a factor of c as well. Okay. Likewise, if I scale v by c, then the determinant of uv gets scaled by c to reflect that. Okay. And here I tried to draw a little picture of like geometry. Why would this be true? So I started in my picture with a vector u and then a vector v. Okay. So the area of this parallelogram, we can think of it as like the base times the height. Here I've drawn the height of the parallelogram in the picture. Now, when I multiply the vector u by c, so what that's doing is it's scaling the base of the parallelogram by a factor of c. However, the height remains the same when I do that. So since the base gets scaled by c, but the height remains the same, the area gets scaled by a factor of c as well. So that's why the area of like the parallelogram formed by cu and v is c times the area of the parallelogram formed by u and v. Okay, so some other properties of determinant that I wanted to mention, this fourth one here. Okay, so I have determinant of u plus v, w is determinant of u and w, plus the determinant of v and w. And then similar over here for this one. You can kind of think of this property as saying that the determinant is kind of distributive. So it kind of looks like you're just distributing w to u and then to v. And likewise for this one, it kind of looks like you're distributing u to v and then to w. Okay. And again, I kind of just drew a picture to try to explain geometrically why these properties would hold for the determinant. So let me try to explain what's going on in this picture. So I'm trying to explain why this one in particular is true. So here I have the vector u, and then here in red is the vector v. Okay. Here I've drawn the height of the parallelogram determined by vectors u and v. Okay. So thinking of u as the base of the parallelogram, determinant of uv would be the base and then times the height, h1. Now, next, for this one, I drew the vector W over here. So then this would be the parallelogram formed by vectors U and W, because this is going to be the same as U. Again, I've drawn the height of the parallelogram formed by U and W. And thinking of U as the base, once again, the area of the parallelogram formed by U and W is B times H2. And then since I have V and W connected head to tail, their sum is a vector connecting from like the beginning to the end. All right, so then here's the parallelogram formed by U and V plus W. And then this would be the height of that parallelogram, thinking of U as the base. So notice that the height of this parallelogram is the same, it's the sum of the two heights formed by these two parallelograms. Okay. So the determinant of U and V plus W, the area of the parallelogram formed by U and V plus W is the base U times the height, which happens to be H1 plus H2. Okay. So that's why this property holds from a geometric point of view. All right, so it's probably not super important that you understand these geometric interpretations, but nevertheless, I'll ask if you guys had any questions about that. Okay. The last property that I wanted to mention was the determinant of these vectors, E1, which is 1, 0, and E2, which is the vector 0, 1. Determinant of these two is equal to 1. Or if you want in terms of like matrices, we're saying that the determinant of the 2 by 2 identity matrix is equal to 1. And here that's pretty clear. If I just draw the vectors E1 and E2, they end up forming a square whose side lengths are equal to 1. So the area is 1, and E1 followed by E2 has a natural counterclockwise orientation, so that's why the term is positive. Okay. Okay, so with these 5 properties in mind, okay, so just a quick recap. Swapping the 2 vectors picks up a negative sign. If you have repeats, it's 0. If you have scalars, you can pull them outside the determinant. Determinant is distributive. And then determinant of the identity is 1. With these 5 properties, we can actually derive the formula for the determinant of a 2 by 2 matrix. So I'm going to do that real quickly just to illustrate how to use those properties and coming up with the formula. Okay, so let's say I want to find the determinant of this 2 by 2 matrix, which I can also do as determinant by acting on the column vectors of this matrix. Okay. Now what I'm going to do here is vector AB. So I'm going to rewrite the vector AB as A times the vector E1, 1, 0, and plus B times the vector E2, which is 0, 1. I'll do the same here. So vector CD, we can write it as CE1 and plus DE2. Now, because the determinant is distributive, so that was like property number 4. Because of that, we are able to FOIL this expression out, if you will. So I can think like we have like AE1 kind of multiplying CE1. But that multiplication is really a determinant of that. And I'm also using the property that the scalars, I can pull them outside the determinant. So I've also done that as well. Now after that, if I kind of distribute this AE1 to the DE2 term, we'll get plus AD, and then determinant of E1 and E2. And then next, if I distribute the BE2 to the CE1, we'll get BC, and then determinant of E2, E1. And finally, at the end, distributing BE2 to the last term will give us BD, and then determinant of E2 and E2 again. All right. So then the second property that I mentioned above said that when you have the determinant of a vector with itself, then that's just going to be equal to 0. The idea being that a single vector by itself forms a parallelogram with area 0. So that term is 0, and likewise this one here, since I have E2 repeated again, that one's also going to be 0. Now, we mentioned how the determinant of E1 and E2, so that's like the determinant of an identity matrix. So we talked about how determinant of an identity is equal to 1. And then finally, for this one over here, because this one is E1, E2, but swapped, the first property we talked about how is when you swap the two vectors, that changes the sign. So instead of +1, this one's going to equal -1. So we put it all together, the determinant of this 2 by 2 matrix, ABCD, is equal to AD minus BC. And so all of that gives us a pretty simple formula for the determinant of a 2 by 2 matrix. All right, so any questions about that? Okay. So now I'm going to kind of generalize all of that. Okay, so now I'm not going to be working in like 2 dimensions anymore. So let's suppose that we have some vectors in Rn. Okay, so the first property, swapping any 2 columns will change the sign of the determinant. Okay, so that's analogous to what we talked about in the first property above. Interchanging u and v, we pick up a minus sign. So likewise, if we like interchange the ith and the jth columns, then that's going to pick up a negative sign in front of the determinant. And the idea of this is just that when you swap 2 columns, you change the orientation of your vectors, and that's why you pick up a minus sign to reflect that. Okay. So then again, kind of generalizing each of those properties earlier. The determinant of a matrix with at least 2 identical columns is going to equal 0. So here, if you had like one vector repeated in say like the ith column and the jth column, then the determinant is going to equal 0. And here the idea is since you have this vector that's repeated, your parallelepiped sort of loses a dimension because of that. And so it ends up being kind of flat in n dimensions. So its n-dimensional volume is going to equal 0. That's the idea of that one. We still have the property that if you're multiplying one of the vectors by a scalar, then you can pull it out to the front. Okay. So scaling a column by some number c will scale the determinant by c as well. Okay. This one I wasn't too sure how to write it in words, but it's the distributive property of the determinant. So when I have like u plus w, so when I have a sum in the first column, I can break it up as like determinant of u with the remaining columns, and plus determinant of w with the remaining columns. And likewise, if I have the sum u plus w, but in the second column, I can also kind of distribute that in a similar way. So do like determinant of v1, u, v3, and so forth, plus determinant of v1, and then w, v3, and so forth, and etc. Okay. And then generalizing the fifth property from above is that the determinant of an identity matrix is equal to +1. And just like how the 5 properties above allowed us to get a formula for the determinant of a 2x2 matrix, these 5 properties will also allow us to get a general formula for the determinant of an n by n matrix. So before I get to that, just any question about any of these 5 properties, which are generalizations of the 5 that I stated earlier for 2 dimensions. Okay. So these 5 properties allow us to derive what they call the quote-unquote big formula for the determinant. And I think the best way to get some understanding of how it works is to just look at another example first. So here I've kind of written it all out for a 3x3 matrix A. So I'll kind of walk you through all of the computations that end up happening in this. So I started out kind of the same way that I did for the 2x2 case. So I take the first column and I write it as A11 times vector E1, 1, 0, 0, plus A21 times vector E2, 0, 1, 0, and then plus A31 times the vector 0, 0, 1. That is correct. So I guess we'll actually see that during this computation. So I'll point it out where that happens. Okay. So I did the same with the second column. It's A12 times E1 plus A22 times E2 plus A32 times E3, and same for the third column, okay? Next, we kind of do the same thing as before, where I would now try to like FOIL all of this out, or kind of distribute all of this out. Now, when I'm distributing, so let's say if I do A11 E1, with A12E1 with A13E1. So that first one is going to be equal to 0 because I have the vector E1 repeated more than once. And so remember, anytime you have like identical columns or like a repeated column, that determinant is going to equal 0. So the next I could have like a A11E1 with like a A22E2, and then maybe like A13E1 again. So that one's also 0 because of the two E1s. So what I've written down here is all the ones that would be non-zero. So A11E1 with A22E2, and then A33E3. Since there were no repeats, that gets us a non-zero term. And then A11E1 now with A32E3, and then A23E2. So that's another one with no repeats. So it's another non-zero term. And then if we take A21 with E2, I can distribute it to the A12E1, and then the A33E3. So that's another non-zero term. And then I can also distribute the second term here to the A32E3, and then the A13E1. And then finally, for the third term here, we can distribute it to the first and the second, or we can distribute it to the second and then the first. Okay? And then all the other ones would have had a repeat, so they all would have been 0. All right, and then after all of that, this would be the determinant of an identity matrix. So this would be equal to 1. So therefore, I have the A11, A22, A33. Now this one, if I swap the second and third columns once, then it becomes an identity. So then because it's like swapping once, that means that this determinant is -1. And that's why I put a negative in front of it. I also, well, this isn't a big deal, but I'm also going to swap the 2, 3, and 2. Okay. And then looking at this one, if I swap E1 and E2 once, then it becomes an identity. Since it has to swap once to get the identity, this determinant is also -1. So that's why I have negative, and then I wrote A12 and then A21 just because. Whoa, okay. And then likewise here, so this one, we have to swap twice. So I swap these two once, and then I can swap the 1 and the 3. So because I swapped twice to get to the identity, its determinant is positive. And then I had A13, A21, and A32. Likewise for this one, swap once, and then swap again. So I have to swap twice to get to the identity. So this one is also going to be +1. And then I have A12, A23, and A31. And then lastly for this one, if I swap the first and the third one, so swapping once gives me an identity. So its determinant should be -1. So then I have negative and A13, A22, and A31. Okay, so that gives me the, I guess this is the big formula specifically for a 3x3 matrix A. All right, so then any questions about that? Hope you guys were kind of able to follow everything that happened. Yeah, so I'll talk about the generalization just for like any n by n matrix, and also do a small bit of the 4x4 case, but not too much of it because it's really long. Okay, so here's the general formula for an n by n matrix. All right, so let me kind of explain that formula. So what's happening is it's kind of similar to what you see here. So you have like A1 and then some number, A2 and some number, and then A3 and some number. So here I have something similar going on. I have A1 and some number, A2 with some number, and so forth. Okay. Now, this, what I have here, this sigma of 1, sigma of 2, and so forth. So the sigma is representing a permutation of the numbers 1 through n. Now, a permutation is just a reordering of the numbers. So like as an example, if I take the numbers 1, 2, 3, 4, and let's say I reorder them, so let's say I do like 2, 1, 3, 4. So that would be like one permutation. I could do like 2, 3, 1, 4, that's another permutation, and so forth. Now, with each permutation, you can associate with each permutation a function. So like with this reordering, I can associate with it a function like sigma of 1 would equal 2, sigma of 2 would equal 1, sigma of 3 would equal 3, and then sigma of 4 would equal 4, for instance. For this ring, we would have like sigma of 1 equals 2, sigma of 2 equals 3, sigma of 3 equals 1, and sigma of 4 equals 4, okay? So that's what the sigma notation is over here in the subscripts. But you can just think of it as it's some reordering of the numbers 1 through n. Now here I have the sign of the permutation. So that's taking into account how some of these were positive and some of them were negative. Okay. So the sign of the permutation is going to be positive, positive 1. If it takes an even number of like swapping to get back to the original order. And then the sign of a permutation will be -1 if it requires an odd number of swapping to get it back to the original order. So this permutation is an odd permutation because I swapped once to get to it. This one is an even permutation because I swapped 1 and 2, and then I swapped the 1 and the 3. So it was 2 swaps, and that's why that one is even. So the sign of this first one is -1. The sign of this one is +1, okay? And if you do that for all permutations or all reorderings of the numbers 1 through n, and add all of that up, that is the like big formula, the general big formula for the determinant of an n by n matrix. All right, so I made a note here that there are n factorial many terms in the summation. And the reason for that is because there are n factorial permutations, n factorial reorderings of the numbers 1 through n. Okay. So now let's take a look at part of the 4x4 big formula. So first, I'll note that there would be 4 factorial, which is 4 times 3 times 2 times 1, which is equal to 24. So there are 24 terms in the summation for the big formula when n is equal to 4. So I'm definitely not going to write out all 24 terms because you don't want me to take the whole review doing this. But just to kind of show you like how you would figure them all out. So I'll do some of them. Okay, so I'm going to start with the numbers 1, 2, 3, 4 written in order. And what I would want to do is I'd want to find all the permutations or all the reorderings of these numbers. So here I wrote down some of the permutations already. And you want to keep track of whether these permutations are even or odd. So this one's even because it takes 0 swaps to get to the original ordering. This one's odd because it was 1 swap. This one's even because it's 2 swaps. If I swap, say, the 1 and the 4, so that's going to be a third swap, so it's now going to be odd. And let's just do one more. So if I swap the 4 and the 3, that's a different reordering from the ones we have so far. That would now become even. So you want to find all of the possible reorderings. I've found 5 of them so far. There are 24 of them total, so you'd want to find all of them. Okay. So then when you're looking for the determinant of a 4x4 matrix according to the big formula, okay, so we're going to have, starting with this first permutation that we wrote down, we're going to have plus A11, A22, A33, A44. And then next, for this one, it's going to be minus. Now it's going to be A12, A21, A33, A44. For this next permutation, it's going to give me a plus A12, A23, A31, and A44. And then for the next permutation that I have written down, it's going to be negative again. A12, A23, A34, A41, and then just the last one, it'll be plus because it's even. A12, A24 next, A33, A41, and then so forth. So again, that's only 5 terms. There would be 24 terms altogether, but that's just an illustration of using the formula, how you could write out after some time, the general for an determinant of an n by n matrix. Okay, so any questions about that right now? Okay, so all right, so the one, okay, so I guess in general it might be good to go over. So Aij. All right, so this is the entry in the ith row. And the jth column. Okay, so when you're looking at all the permutations, the way the big formula works is they all go into the second entry or the second subscript, so it's like the column. And then just keep the first subscript like always 1, 2, 3, 4 for each term. Okay, so you're only permuting or reordering the second subscript, if you will. And then you always start with the A1, A2, A3, A4 for the first subscripts. Okay. All right, and then let me do one example. And because the formula is so big, I'll just do one example using the big formula for a 3 by 3. So I'll keep the formula in the screen over here. And then I'll just do one example using 3 by 3 matrix on the right over here. Okay, so I'll make up some numbers right now. Let's do 1, 2, 0, -1, 1, 3, then 2, 1, and -1. Okay. So if I try to compute the determinant of this 3 by 3 matrix using the big formula here, so this A11, A22, A33, so that would be the product of these three entries. So that's going to be -1. Okay, so this A11, oh, actually, I'll tell you what, let me do all the ones that were plus first. So let's look at this one next, A13, A21, and A32. So that's going to be A13 with A21 and A32. So multiplying these three together will be 0. And let's do this one next. So it's that one is oh yeah, this one. So A12 is this one here. Oh, did I do that wrong? So A13. Oh, sorry. This one A13 is actually over here. So that's my bad. First row and third column. So it's going to be 2, and then A21 and A32. Okay, so this one times these two is going to be plus 12. This one over here would be A12, A23, and A31. So that one's the one that's 0. Okay. So those were all the ones that were plus at first. Then I have the ones that are all being subtracted in the formula. So let me start with this one. It's A11, and then A23 and A32. So I'm going to do minus the product, so minus 3. And this one is A12 over here with A21 and A33. So the product is 2, so I'm going to have minus 2. And then finally, this last one that's being subtracted, it's A13, so this one. And then A22 and A31. So minus this product, so minus 0. And then adding all of that up, it's going to be 11, 8, it's going to be 6 altogether. Okay? Now I'll make a small comment about, at least for the 3x3 case. So if you go back and check the first 3 that we did, the ones that had a plus sign in front of them. Okay, so those 3 correspond to multiplying these 3, and then these 2, or these 3, and then these 3, which gave us this one. So if you kind of like think of like going along a diagonal from left to right, that gets you the first 3 terms. And then for the last 3, which are being subtracted, if you go from right to left, so like here's one diagonal, so that one gave us this minus 3. And then doing these 2 with this one gave us the minus 2 over here. And then doing these 3 from right to left gives us the minus 0. So that's kind of like a useful way of kind of remembering which ones get added and which ones get subtracted. But this idea only works for a 3x3 matrix though, so don't try to do it for something larger than 3x3, okay? All right, so any questions about how we got the determinant of that 3x3 matrix using the big formula? Yeah, okay. So, because the big formula is so big, we don't necessarily use it often for computing determinants. So let's talk about some other ways that we can compute determinants. So another method that you guys learn is computing determinants. Using the cofactor method. Okay. So this one, I'm not going to really explain much like why this formula works. So just have to take it for granted that it's equivalent to the big formula that we derived above, okay? Here's how this one works. So I have an n by n matrix A. And we're going to define the ij cofactor of this matrix A, which I'll denote as a C for cofactor and then subscript ij. So this is equal to -1 to a power of I plus j. and then times the determinant of the matrix obtained by removing the ith row and the jth column of A. All right. So then using these cofactors, it turns out that you can compute the determinant of A by choosing any row or any column. So let's say if I choose the ith row, what I can do to compute the determinant of A by using the ith row is I take each entry in the ith row, so AI1, AI2, AI3, and so forth. And take each entry in the ith row and multiply it with its corresponding cofactor, so CI1, CI2, and so forth. So if I add all of those up, it turns out that that will also give me the determinant of A. And instead of going along one of the rows, I can also go along one of the columns as well. So if I did that, I would take each entry in the jth column, so like the A1J, A2J, and so forth. So take each entry in the jth column, multiplied by the corresponding cofactor, and then add all of those up. And it turns out that this will also give you the determinant of A. So it doesn't matter which row or column you choose. You take all those entries, you multiply them by the corresponding cofactors, add everything up, you're going to get the determinant of A. Okay. So let's see how to use this method for computing the determinant of a 3x3 matrix. So let me use the same 3x3 matrix that we did earlier. Okay. So earlier we computed the determinant of this 3x3 matrix, and it happened to be equal to 6. So let's confirm that we get the same results using this method. And now, first things first is I'll make a quick comment about the -1 to the I plus j in the formula for the cofactor. So there's a kind of useful way of remembering whether that's going to be +1 or -1. So here what I'm going to do is I'm going to draw just a little picture. So I'm going to draw like a 3x3, and I'm going to start with plus, minus, plus in the first column. And then I'm going to just kind of alternate now in each row. So plus, and then alternating will be minus and then plus. Here, since I have minus, I'm going to alternate, so it'll be plus and then minus. And then since I have a plus here, alternating, I'll have minus and then plus. So this picture of plus and minus signs will tell us whether the cofactor is going to be like +1 or -1 here, okay? All right, now let's see. So with that in mind, let's try to compute the determinant by using this cofactor method. So I'm going to compute this maybe 2 ways right now. So first I'm going to go along the first row, okay? So along the first row, I'm going to take these numbers starting with 1 in the first row. So I take this, and then what I'm going to do is I'm going to, in my head, cross out the first row and the first column. I'm going to take the determinant of the remaining 2 by 2 matrix here. Okay, so next I'm going to take the number -1. Now cross out the row and the column containing it. Take the remaining 2 by 2 and take its determinant. And then take the last entry in the first row. I'm going to now just cross out the row and the column containing it. Take the remaining 2 by 2. And then for the sign of the cofactors, whether it's plus or minus here, I can get that from this picture. So along the first row, it should be plus, and then minus, and then plus. Okay. Now these are 2 by 2 determinants. So remember the formula for a 2 by 2 determinant. It was A times D minus B times C. So now it's going to be 1 times -1 minus 3. Here minus negative, so I'll do plus. And then -2 minus 0. And then here we have +2. And then 2 by 2 determinant, so it'll be 6 minus 0. Okay, so if we compute and add all of this up, it's going to be -4 minus 2 plus 12. So altogether, we get a final answer of 6, which is the same answer that we got earlier using the big formula for a 3 by 3 matrix. Okay. And then just to kind of drive things home, so I said that we should be able to do this for any row or any column and get the same result. So I did it along one of the rows. Let me do it along one of the columns now. I'll do it along the first column. Okay. So doing cofactor expansion along the first column. So I'm going to take the entries of the first column, the 1, the 2, the 0. Now for the 1, if I cross out the row and the column containing it, and the remaining 2 by 2 determinant, then I cross out the row and the column containing these 2. I take this remaining 2 by 2 now. And then I take the last entry, cross out the row and the column containing it, take this remaining 2 by 2. And then for the signs, if I'm going along the first column, plus, minus, plus. Okay. And then working these out, so this determinant is -1 minus 3, so -4. And then here we have 1 minus 6, so 1 minus 6 is -5. And then this last one should be 0. Just because you're multiplying by 0. So then we have -4 plus 10. And again, that gives us the same answer of 6 for the determinant. Okay. All right, so any questions about computing the determinant using cofactors? Okay, yeah. Yeah, so certainly after you do it a couple of times, you tend to get the hang of it pretty quickly, I would say. So one thing that you notice from this example is that if you choose a row or a column with a lot of zeros in it, it's going to make your life easier because the zeros are just going to like zero out one of the terms in the summation, which means that you'll have less computation to do. Okay? So it's always best to choose a row or a column with as many zeros as possible. Yeah, for sure. Yeah, so like I said, people don't tend to use the big formula much for computation. The big formula is kind of good from a theoretical standpoint, especially because we derived the big formula using all the like geometric understanding of what the determinant represents. And although I'm not going to emphasize it too much for the rest of this review, it is important to remember how the determinant has this geometric interpretation as being like the area of, or sorry, the volume of the parallelepiped formed by like the columns of your matrix. Okay, so I'm going to mention a couple of things right now. Just a few facts. The first fact I want to note is that the determinant of a triangular matrix is equal to the product of its diagonal entries. Okay, so when I say triangular, that means it could be upper triangular or it could be lower triangular. As a special case, this also applies to diagonal matrices because a diagonal matrix is both upper and lower triangular. And just to see why that would be true, let me just like draw a generic upper triangular 3x3 matrix. And let's imagine that we wanted to compute the determinant of this 3x3 upper triangular matrix. Quick comment about notation. You'll see people draw like a vertical line instead of like a bracket if they're intending to compute the determinant of the matrix. So that's why I'm drawing a vertical line because I'm going to compute the determinant. So if we do the expansion along the first column, we will get A times, then take the remaining 2x2. Okay. And then the rest of the terms that we're adding will be 0 because of the zeros in the first column. And then when you get the determinant of this 2x2 is just df. So altogether, the determinant is a df, so the product of the diagonal entries. Okay. So similar computation proves the general result for any triangular matrix. Another fact that I'll note about determinants right now is that the determinant of A and the determinant of A transpose. So both of these are the same. It's kind of reflected in the fact that when you're computing the determinant using cofactors, that you can choose any row or any column, doesn't matter, and you'll get the same result. So that kind of ties into this fact that A and A transpose always have the same determinants. Okay? And then I'm not going to work it all out, but just to show you how you could do things with a 4x4 matrix. So let's say that I were to just set up computing the determinant using the cofactor method. Okay, so first I want to just determine what terms will be added or subtracted when I do the cofactor expansion. So let's start with just using plus minus signs along the first column. And then I'm going to now alternate along each row now. So here I'll get minus, plus, minus. Here I have minus and then plus, and then minus and then plus, and so forth. So minus, plus, minus, and plus, minus, plus. Okay. So then I can pick any row or any column. Let's say I pick the first row. Okay. So I take, starting with the 1, it'll be plus. And then I cross out the first row in the first column, take the remaining 3x3 matrix, and I would need the determinant of this 3x3, which I could then try to compute by doing like another cofactor expansion, for instance. Okay. Next, I'd have like a minus 2. Now cross out the row and the column containing the 2, take the 5, 7, 8, and so forth. And now you need the determinant of this 3x3 matrix. And etc. Okay? So as you can see, the cofactor method also gets pretty unwieldy once you get to a 4x4, unless you had like a lot of zeros. All right? Okay. So then if you wanted to compute the determinant of, say, a 4x4 matrix like this or something bigger, there is another method that we can go about for computing determinants. And this method is probably for us going to be the quickest and most efficient way of getting the determinant of larger matrices. Okay. All right, so what we can do is use some row or perform some row and column operations to make it a little bit easier to compute the determinant. So first, let's talk about how row and column operations affect the determinant. So we primarily do row operations. I'm going to focus on row operations when I'm talking about this next part. But the same holds if you were to perform some column operations as well. Okay. So thinking about the types of row operations that we might perform on a matrix. So as we know, one type of row operation that we can perform is to just swap two rows. So swapping two rows will change the sign of the determinant. This is analogous to how we talked about swapping two columns will change the sign of a determinant. That was one of those 5 properties when I was talking about the big formula earlier. So the same is true if you swap two rows, it changes the sign of the determinant. Another property, another type of row operation that we might perform is we might multiply a row by a scalar. So multiplying a row by a scalar c will also multiply the determinant by c as well. This is actually also analogous to one of the 5 properties that I mentioned earlier for the big formula. And then the type of row operation that we tend to perform the most is, we add a multiple of a column, or sorry, we add a multiple of a row to another row. So when we perform this type of row operation on a matrix, it turns out that this row operation does not change the determinant at all. So adding a multiple of a row to another row does not change the determinant. Okay. So to see how we can use this information, so let me take, again, just that same 3x3 matrix that we had earlier. Okay. So let's say I were to perform a row operation right now. Let's say if I do maybe row 2 minus row 1 first, or sorry, minus 2 of row 1 to eliminate this 2. And then let's say I do one more row operation, which I do row 3 minus row 2, just to get it into maybe like the usual upper triangular form. Okay. So according to these 3 rules that I wrote down, here all I've done is add multiples of rows to other rows. So that doesn't change the determinant. So what that means is that the determinant of this matrix A should be equal to the determinant of this matrix U. Okay, so determinant of A equals determinant of U. But because U is an upper triangular matrix, we know that for a triangular matrix, its determinant is the product of its diagonal entries. So then determinant would be 1 times 3 times 2. So it's going to be equal to 6, which once again is the same as what we have seen previously. Now, something that you do want to keep in mind is if you perform some of these 2 operations, then you do need to be careful about how the determinant has changed since you performed those operations. That is also going to be true if you are able to find an LU factorization of a matrix A. which you can't always do. But if you are able to find the LU factorization, then it would be true that determinant of A would equal determinant of U. Okay. So if you were not able to get the LU factorization, that means that you had to swap some rows, and then you need to be careful about whether you picked up like a minus sign from doing the swapping of the rows. Okay. Okay, and let's see here. So this method of, for instance, reducing your matrix to get some more zeros, or performing some row operations to get more zeros in the matrix, this is the best thing that you can do for calculating the determinant of larger matrices. Get some more zeros by performing row operations. If you reduce all the way to the triangular form, you can then do like the product of the diagonal entries. Something that you can also do is like if you just do enough row operations to get like zeros in the like first column like this, for instance. Once you have like enough zeros, you can then try to start the determinant by doing like cofactor expansion along the first column. And then every term would be 0 except the first one where you have like 1 times this remaining 3 by 3. So like you don't have to reduce all the way to triangular form. If you just get a bunch of zeros in a row or a column, you can then start by like doing the expansion along that row or column. Okay. But altogether, the idea is get some more zeros by performing row operations, and that will make your determinant easier to compute. Okay. Okay, so then with that, I'll just say a couple more things. So additional properties of the determinant. So in no particular order, I already mentioned, but I'll just restate it, how A and A transpose will have the same determinant. Okay. If you have the determinant of a multiple of the matrix A, okay. So thinking about this one, when you multiply a matrix by a scalar, you multiply each entry by that scalar. So you can kind of think of this as like multiplying every row by C or multiplying every column by C. So if A is, say, size n by n, so you multiplied all n rows by C. So each of those would have multiplied the determinant by a C. So since you did it n times, you're going to have a total factor of C to the n times the determinant of A. Let's see here, some other properties. So this one's kind of interesting. So the determinant of a product AB is equal to the determinant of A times the determinant of B. Okay. So if you try to think about it just in terms of like either the big formula or the cofactor method, or even the row operation method, it's probably not clear at all why that would be true. But this one, I don't have the time to go into it, but this one has a very, very important geometric interpretation to it. But I won't be able to go into it, so I'll just state it like that. And then some other properties of determinants is as kind of a special case of this formula, when you have a determinant of a raised to a power, so according to the third property, that's determinant of a times the determinant of a times the determinant of a, and so forth, k times. So it's just determinant of a raised to a power of k. Yeah, so now I guess maybe a small caveat just to be sure is I am assuming that A and B are both like square matrices, the same size. And just to emphasize like why that would matter is, let's say that A is size like 2 by 3 and B is size 3 by 2. So if you look right now, like AB would be size 2 by 2 altogether, and BA would be size 3 by 3. So in theory, since both AB and BA are square, you could compute the determinant of both of these products. But you cannot say that it was equal to like determinant A times determinant of B, because the determinant that we found only works for square matrices. And it turns out that in a situation like this, it is not always the case that the two would equal each other. Okay. But if they are both square, then yes, determinant of AB is determinant of A times determinant of B. And likewise, determinant of BA would also be determinant of B times determinant of A. So they would be the same in the case where they were both square of the same size. Okay. Yeah. All right. And then finally, I'll mention one more property of determinants. And so the determinant of a matrix A is going to be non-zero if and only if A is invertible. In such a case, you can get the determinant of A inverse as being 1 over the determinant of A, which if you want, you can also think of as a determinant of A raised to a power of -1. So in that sense, you can kind of think of 5 as like an extension of 4 when A is invertible. Okay. And I'm just going to do just like a super quick example, and I'm going to end my review after this one. So let's say I have 3 matrices, A, B, and C. Let's say all of them are size 4 by 4. And then let's say determinant of A is 3, determinant of B is -2, determinant of C is maybe 4. And then I want to know what is the determinant of 2 A transpose B squared and C inverse. Well, if I just use the properties that I've mentioned over here. Okay, so this 2, I can pull it outside of the determinant, but it'll get raised to a power of 4 because everything was 4 by 4. So that's the second property here. Then using the third property, I can say this will be determinant of A transpose. Determinant of B squared. And determinant of C inverse. And then we know determinant of A transpose is the same as the determinant of A, so that's just 3. Determinant of B squared is determinant of B all squared. And then determinant of C inverse would be 1 over the determinant of C, so 1 over 4. So then I guess these would cancel. So final answer would be 16 times 3, so 48. Okay? So just like a really quick example illustrating some of these properties in action. All right, so with that, are there kind of any last questions about anything related to determinants? Okay. So I'll go ahead and end the recording.